Okay, so the next experiment is the Thomas Townsend Brown gravitator. This came out from a patent in 1929. And many people talk about electrogravitics and they talk about Bifield-Brown effect, and then they show a video of a lifter. Nothing can be farther from the truth. The gravitator has nothing to do with lifters. Lifters are not anti-gravity. They do produce ionic wind, but they are not anti-gravity. So what is inside this patent? I cut out all the pictures. I'm not going to get into all the words. There's way too much over there. So basically, here's the first experiment he did, which was he had a glass rod in between two 44-pound balls, and he placed 120,000 volt potential across them, and there was a direction of movement toward the positive. And he tried this encapsulated in oil, and there was a direction of movement toward the positive. And he also set it up like this, where it was spinning. But here's what's interesting about this experiment. It would move toward the positive, maintain that that spatial differential, like if it was producing however many grams it was producing to swing that much. Then over time, with the voltage maintained, with the potential maintained, it will slowly come back toward center, and it would like lose its anti-gravity effect or whatever that was. Which is something very strange. We tried replicating this experiment several times and haven't been successful. So let me show you what we've done. And then we'll get into why it wasn't successful. And this is something that we just realized pretty recently. So here's the insulators. And he also mentioned that the weight of the dielectric affected the amount of effect that he was seeing. And he was using insulator sheets, and there was lead sheets as well for the metal. So he wanted to make this thing as heavy as possible because he thought it was a gravitic effect. Okay. Here's and in this description over here, he talks about using bakelite and litharge. Litharge is basically lead oxide powder that was mixed inside the bakelite, which is kind of like epoxy. And that we actually found out might have been the reason why this thing moved. And that connects in with the Banduric complex high voltage field generator device that Jeremiah is going to be presenting on in a little bit. Jeremiah, I know you were playing around with litharge a bit, were you?
Yeah, let me find my mouse here. Yeah, we took some litharge. We were expecting it to show up as a fine powder, but it actually showed up as kind of large clumps, like much larger than sand grains. So we dedicated a poor and helpless coffee grinder to chopping it into very, very fine powder, which worked fantastically, in fact, and didn't kill the grinder yet. So we wanted the finest particles to be mixed in as possible, and we were looking for heavy mass material. So we have lead plates that we want to rebuild this device with. We actually took some time. What is it about? I don't know if you have pictures of the crazy array of the fishing line or the clothesline that we had hung up. But yeah, we coated a whole bunch of papers in lacquer so that we could test something closer to the materials that he was actually working with. They're leaky dielectrics, and we think that the ability of the dielectric to leak in Brown's case may have actually been important. But of course, we haven't gotten one to work yet, so we still don't know. We sure have tried a lot of things, though.
Yeah, I think I have the pictures of all that paper that we were working on. I might have stuck it in the end, not in the right order, but this is
labor of love.
Yeah, it was a pretty crazy experiment. We hung a whole bunch of papers all the way across the shop, and we were spray painting them with lacquer. We're trying to do the experiment as true to the experimenters, what he actually did, versus trying to take shortcuts and use modern materials. Because like Paul said before, if you think you have this whole theory and you try something completely different and it doesn't work, you do a 4-inch disc instead of a 12-inch disc, for the spinning pod column experiment, then, you didn't replicate it. You can't say it didn't work. So this is an experiment that we've been playing with for quite a while, trying all different kind of stuff. And I'm going to get into some other stuff I tried. This is the first experiment I ever tried, actually. dirt cheap. I just 3D printed this flying saucer shaped device and put some washers on either side of it and charged it up with an array of these high voltage amplifiers that you found on eBay that came from China, and ran that through an X-ray rectifier system, and it moved a little bit. Here's a this is that same Teflon piece that we had earlier, and you can actually see a little burn mark there. That's where that's when that happened. So when this happened, I was playing high voltage on it. This was all done in my garage before I moved it into the shop. So I've been doing this for a couple of years already. There's a big strike of lightning. You can notice it's in the same spot. That's probably where we got that weak point that eventually burnt through the Teflon. Okay, and the next experiment was, what if I created a device that had these sharp pulse in one direction and a slow inclination back in the other. The thought process behind this was the Podklanov gravity impulse experiment, where he noticed that every time you multiplied the voltage, you got a 10 times increase in the effect. So I thought, what if I pulsed just a regular parallel plate capacitor, or some fancy shaped or an asymmetrical capacitor with a similar waveform where it's a slanted offset sawtooth wave, what would happen? And here is the experiment. I had 4 vacuum tubes in series, and I'll just play the thing.
Okay, so this is the first test of the full experiment. We have 4 vacuum tubes independently powered with a lot of dielectric connected to a high voltage power supply, which is putting out 125,000 volts maximum. The diodes are being controlled via fiber optics via this signal generator box. And there we have the subject, basically a copper cone on top of a Teflon dielectric with a piece of silver at the bottom. And there's a little barium titanate to make it into a bit of a capacitor. And then we have a scale at the bottom. It says 180, I think 184, that's grams. I don't know how accurate that scale is. Whatever, we'll see what happens. Rig this up so I can.
Or powering up the power supply.
Volts.
Okay, so that was what was the pulse device? Okay, it's moving in the wrong direction now. The results are pretty inconclusive. The scale did go a little crazy, although it did show around 30 grams of weight loss. I don't trust those numbers because the scale was going crazy. And this is an experiment that I want to replicate again. You could also hear that the vacuum tubes, even though there was 4 of them, wasn't holding back the voltage properly. That was because I had the grid voltage on the triode, which basically shuts off the electricity, only at 15 volts. We had to add another, I should have added another a DC to DC converter to get a potential of like 200 volts on that grid to really shut it off properly. Also, those tubes that I had in that experiment were only capable of around 5 watt output. So we really need to go with something a little bit more powerful in order to do this experiment at any higher power. So I can still replicate this at 5 watts, but I don't know if there's any point. Here's the view from underneath. It looks kind of cool. Looks kind of like a flying saucer. Too bad it's out of focus. And basically, you're seeing the voltage as it rose past a certain point, it would break down. Okay, so here's the next step in the gravitator experiment. We built a gravitator or parallel plate capacitor, basically with sheets of copper and glass as the dielectric. Again, this is not exactly what Bifold Brown did, or T. Townsend Brown did. And here's the different layers. We're adding more layers. Put a cap, put a hole, total weight. Here's the setup. Now, who can see a problem with this setup? So this is the grounding wire over here. This is the spy camera, so we can see what's going on. And over here is there's 2 wires. One of them is for voltage sensing, and one of them is for voltage delivery. Well, the problem was, well, here is the spy cam, and we had the smoke going up to verify that it was actually moving. There was no ionic wind, and it passed all those tests. It was moving back and forth. Here, move it a little forward. You can see it. I was able to create some sort of isolation there. Definite movement increased as I changed the voltage. But what we discovered, unfortunately, was that this was happening.
Go ahead, power it up. Now down. Definitely that's what's happening.
Electrostatic repulsion between the 2 wires. So that setup wasn't done correctly. And then we moved on to eliminate that. We had just 1 wire going to a Teflon rod that was hanging from the ceiling. And then there was a thin wire that went into the gravitator, eliminating all those problems. The ion wind still wasn't there, but still wasn't present, and it did not move at that point. Here is an experiment we did with a parallel plate capacitor, and over here is a layer of epoxy with barium titanate in it. So I thought maybe adding a little bit of oomph to the capacitor will change it. The high K value material. That didn't work. Nam Tran, he's our buddy out in Vietnam, and he kept on running this experiment and was getting positive results, and he would show us videos and stuff, and wanted to send us the his gravitator device that he had made, and see if we get any results. So he shipped it all the way from Vietnam, and here is that experiment. We ran it.
Hey guys, we are at Falcon Space over here, and I have NAM's capacitor set up, and that is the force meter. that is a scale. It's grounded to the ceiling. We did separation of the high voltage cables using Teflon and PVC pipe and a box of mailer strips.
You see the wires here by shining the light down them. So there's the wires that they came with. There's the ground wire. It'll be receiving 30,000 volts positive, and we will see what we get.
We also have a incense stick over here just to see where the airflows are in correlation to it. Okay.
All right, here we go. 3, 2, 1. Oh wait, power. Hello. 3, 2, 1.
Definitely showing some airflow.
Powering down. 3, 2, 1.
Airflow is definitely changing, but there was no change in weight.
So one more time.
Yeah, so basically this didn't work in this configuration. The next thing we looked at was his power supply, NAM's power supply. He was using a rectifier system. And, oh, Jeremiah, why don't you get on? You can talk about this as well. We noticed that his power supply system was built incorrectly, and therefore it was creating a DC bias with a like an AC form on top of that. So we thought maybe that had something to do with it. And we're trying many of our experiments with a similar power supply to see what would happen. Now let's move on to the next one. Oh, Jeremiah, these
are. Yeah, the time-consuming papers.
Yes, these are the time-consuming papers. I have them right behind me. They were hanging across the shop for a couple of days as we let them dry out.
So this is just to prove that we do our paperwork correctly.
Yeah, we definitely did our paperwork. Here's another device. This is more of an ion wind thing. Just show you it real quick. This is something that was inspired by T. Townsend Brown.
Hey guys, welcome to Falcon Space. Today we're doing our first experiment inside the Faraday cage. We're doing a simple charge up of the capacitor to see if there's any movement. We don't expect much to happen, but we just want to see what happens. I'm seeing activity. We've got motion. Got a considerable amount of motion on the wires. Not much. Oh, we got an overflash. What'd you go up to? There you go. Right where we expected. What are you at now? All right, another flash again. We're getting rotational motion on the unit. It's looking to me like ion effect, but I could be wrong. You got another flash over? Are you recording the voltages?
I'm basically pulsating at 50,000.
50,000 pulse, okay.
I'm going to let it relax now to 0.
Okay.
Pulse at 50.
All right.
Basically, it would just move back and forth, like you can see. And if you heard the little noise in the background, that we were doing this experiment right when SpaceX did its first landing of the Falcon Heavy, and the 2 rocket engines came down as we were doing this experiment. So it was kind of cool timing. This is another experiment I ran. This was back at the house in the garage. I had one of the vacuum tubes hooked up to a secondary of a Tesla coil that basically sparked that little spark gap over there. And there was a piece of bismuth out here. I don't know what I was thinking, but we tried it and we had a laser pointing on that to see if there's any deflection. Nothing happened. Okay, mercury vortex engine. This is the next experiment. This is a video from the internet. This is not ours. Just to show you the basic concept. Okay. Pour the mercury in, apply voltage, nothing happens. You need to add the, what's he adding there? I think he's adding salt, so you can see it move around. But that could have been barium titanate. And as soon as you add the magnet, it starts to spin. Well, the purpose of spinning mercury, as far as I believe, is really has to do with the complex gyroscopic spin. So you wouldn't be just doing it in a circle, because that would just make a regular gyroscope. What you really want is some complex spin, maybe with fancy tubing, and we can use some advice on how to shape that and why it would work. Okay. The next one is, these are the electric experiments. Go for it. What do we got here? We're making electrics here in the lab.
There it is, one ugly piece of very warped plexiglass, but generally not bad in the center area. In fact, it's kind of like an art piece. Anyways, it ended up working out pretty well. You can see the profile of the pieces that were set as the electrode plates. And the big question I have is, was this actually hot enough during the making of this electrode? That's one question we do not have an answer to yet. But supposedly,
Our first working electric, it is made out of acrylic, and you can see the sides of it are not the electric in the center over here. An electric is basically a magnet for static electricity, and we have it covered in aluminum foil, and watch what's going to happen as I bring the aluminum foil closer. It grabs onto it like that.
there's charge on the surface that's causing this maybe to be attracted to not only the scale and its surface, but the table beneath it.
You think?
Yeah, I think, because if we do, some more of this sparking and arcing,
They're crazy.
it is what it is. So,
That doesn't hurt.
of course it hurts. Just used to it. Okay, but here's the issue. So we've seen what, a gram of difference before, right? Now what do we have? Now we're spaced away.
Ooh,
Look at that. Okay, let's see. 62.277. We'll flip that over. Try not to tip it over this time. Yeah, this platform not made for this. Let's see. 62.34, 60, let's see. 62.34. Look at that. Pretty much the same.
So basically, we discovered that if you put a electrode directly onto a scale and it's close to the table, it will be attracted to the table in one orientation and repelled in the other. So it's not really anti-gravity, if that's what we're looking at. That was the conclusion of the electric experiment so far. The next one is the complex gyroscopic spins. And we went through 3 iterations of this experiment. This is the first one. We're powering it up.
Okay, this is our first.
I got a question, Mark.
Oh, go ahead.
Did you guys take into account the fact that the styrofoam cup is a material that has styrene has a very high negative bias?
Oh,
for,
actually, I
static
can answer that
electricity?
question
Oh,
for you.
yeah.
What we ended up finding out is that it wasn't so much an effect of the styrene cup. It's just that there was so much electrostatic charge on the surface of our pseudo-electrets. They didn't really work all that well, so I'll just premise with that. But when we took them out of the system, they had quite a bit of charge on them. And we noticed that the electrostatic attraction to the surface of the table was the biggest contributor to our measurement errors. So when we tested what we had so far at a reasonable distance from the table, and the highest that we tested was about 2 feet away, then we didn't actually notice any difference between one orientation or the other, or any difference between a high level of charge in the other, and that's with a 0.01 gram of resolution. So we clearly didn't get it right at the electrolyte level.
Oh, okay. And this is Tim. If I could jump in really quick, we're running over a little bit on time, so let's hold questions until the Q&A session afterwards.
Okay, yeah, I know there's a lot of information here. So if you guys have any questions, I think the best thing to do is put it in the chat, and then we can answer them one by one. If you just put all the questions in the chat, you'll probably think of something as we're moving along. Throw it in there, and this way you won't lose your train of thought as we move forward, because we're going through a lot of material here.
Handle device, gyroscopes. So they don't fire. And they're all turning. Gyroscope. And this thing sounds really cool when you power it up.
Yeah, let's turn some more shit on. I want to see this. This is great.
So we have it on a
Here you can hear the gyroscope
pendulum
slowly
torsion
turning on.
balance.
We had to put a row of resistors in there because they were turning on too violently when we just powered them up straight. So now it's running through the row of resistors. When I turn the resistors off by shorting out the circuit, you're going to hear them go into high gear. 3, 2, 1. I'm going to power on the remote control. And now we're going to go power on the servos. 3, 2, 1. There we go. Just stabilize the device. Like I mentioned earlier, this device is not very stable. The gyroscopes are being held by these tiny little servos, which are not adequate. But we will try it regardless.
Yeah, I can see a lot of instability in those motor mounts and the servo mounts well, that was a little hyperextended there. You got some
We got
collisions
a
on there.
lot of shaking going on here.
Again, we need to eliminate that static friction point there to make sure it's not just pushing off of that as a pivot point. Because any kind of place in the system where you can have a buildup of static friction, and then a sudden release of static friction, we will create a push point where you can push
Try to
off of.
stabilize it a little bit.
But this is interesting because it has turned. It has rotated about 30, 40 degrees so far. There, it just rotated backwards, and now it's also colliding with the pin in the center. I think they need to be mounted.
They need to be mounted differently, yeah.
So we'll have to.
This is a work in progress. I wasn't
We'll
really
have to
expecting
rework
this
on
to
that
work.
one. But yeah, that's cool that you set that up. That was cool. People want to see stuff like this. They want.
I don't know, man. I really want field propulsion. I want field propulsion with thermonium parts. That's the ultimate goal.
Now we're trying with just one gyroscope.
Check this out. It is working. Tom here is at the controls. He's trying to use just one gyro to make to get it in resonance with the device. I don't know if that's actually field propulsion if you're going in resonance with the entire setup. But we are getting.
Wow, he's nudging it forward, inching it forward.
Just one gyro is being controlled right now.
Sound good?
Craft prototype V.
On this device, I'm going to skip it. It was only 2 gyroscopes, and the thing just went
Gyroscopes are
crazy.
spinning.
But the mounts for it were the second iteration, and they worked perfectly. You can see it's just making a big mess, moving all over the place. Finally, we have all 3 of them. It's a little over zoomed in. Sorry about that.
It is kind of like rotating around a little bit, pushing it a little bit, man, So if this is the kind of motion that we need to do, and we can do it with these like 2 little gyros, and it's propelling this thing a little bit, right? Now imagine if we took the same kind of motional effect and we started doing it to all the little spin orbits of these electrons or atoms in the surface of our spin coating, our smart skin, right?
So I think what Jeremy may have been alluding to is where inertial mass comes from, because that's exactly what's going on. You have all these random spins, and when you move the object, you change the random spins of the subatomic particles. or if you change the subatomic spins, you might be able to move forward as well. So they probably goes both ways. The experiment needs to be ran again. We need to get rid of that static friction, like we said, and the device is up here on the right. And that's something that we're going to be working on in the future. The next experiment is, ooh, looks like we skipped a picture or something like that. This is, okay, this is the video from the, some of these things came out of order. This is the spinning easy Alzaphon thing. You can,
There it is.
you just
Got
see
the
how-
full throttle to the replay, see what happens.
It's like a 1 horsepower motor in there. That's from the easy Alzaphon experiment. Now this next thing is the mercury. This is our work with mercury when we set it up. Some of these videos came out of order. I'm sorry.
Go for it.
Let's make it spin real quick. So you got to take that out of there. I'm going to give you the Dremel. You got it?
So we achieved some movement with mercury. Should have been with the mercury experiment. Oh, and this is NAM's take on the Searle device. We did he did a couple replications and didn't see much of an effect with a 4 rollers set up, and he was applying high voltage from the side over here. Okay. And oh, this is me and Jeremy getting arrested by the Men in Black at Alien Con. Okay. Oh, okay. Sorry for that. There was some mix-up with the order. So right now we're looking at the PodClonv experiment. This is the PodClonv impulse experiment, and it basically states that when you have a bilayer superconductor and you impulse it with a lot of energy, or Marx generator, it creates a gravity beam, and the superconductors need to have what's called a it's like a barrier, a Josephson junction barrier in between the two superconductors, and that's what helps allow all the electrons to go through one superconductor to the next simultaneously, and that puts a drag on space-time or something like that. I don't know how it could possibly work, but we are trying it out here.
Yeah, we're connecting together some nickel metal hydrate modules here to power the coil for this take on the PodClonv experiment. And I think Jeremy got into this earlier. There's different types of PodClonv experiments. There's also different levels of of things that you can add to this experiment, such as putting it all in a vacuum. That we weren't able to do yet. It is pretty difficult to set up something like that. But we do have it inside of a coil, and we are impulsing it with a large amount of current rather than a super high voltage. So this is 613 joules of energy going into the superconductors via a thyrotron.
Get rid of that menu. Oh, sorry guys. Does it look all right? You see that? Also, you want to talk a little bit about your vacuum tube again?
Oh, so this is the thyrotron that came out of the
linear.
Yeah, the Berkeley Labs linear accelerator. So this actually came from Berkeley, and they took apart the accelerator and sold it on eBay. And I actually built this this whole setup in order to power it. This entire device is going to be floating at around 35,000 volts. So we have a high voltage Faraday cage here, and there's all different types of electronics needed to power the tube. You have to give it some a static voltage of 6.3 volts, and then you have to apply a high voltage grid that's all controlled via a fiber, basically a light sensor over here. So we're going to shoot a laser through the side in order to trigger it. It's going to be a pretty cool experiment, and we hope to see the results in a pan on the floor.
Jeremiah, do you want to show us what you worked on today, this thing right here?
Yep, inside there. We've got a brass bolt, taper head Phillips, soldered to a copper disc that's 1 millimeter thick, as wide as the YBCO discs, which are 1-inch discs. And they are bonded at 3 points. So we have a proprietary bonding agent combined with CCTO, calcium, copper, titanium oxide, I think, and nickel silver powder. And then we have just a plain PBO in the middle. And on the other side, we have a mixture of the PBO and a copper powder. And the reason why we're putting the metal powders in this material is the PBO is actually not very conductive. So by cramming them full of these metal powders and sandwiching these plates on the ends of the YBCO, we're able to get some connection to the surfaces of the YBCO, which are ceramic and very, very hard to bond to. And so the other side is just a duplication of the first side, except for the bonding agents between them. And then that's sitting inside of this little chamber here. So I'll pick that up for a moment to kind of show you what's going on here.
Careful with it.
So earlier, your cameraman right now, Mr. Alien Scientist, cut out these 2 wood discs for us, and we screwed them together with 8 standard household screws to create a nice bobbin, which we wound by hand. This is 13.5 gauge, very heavy build insulation copper wire. And inside of the center is a piece of PVC to insulate the voltage, and then that assembly. You can see the top of the bolt there. The top of the bolt is one of those brass bolts shown in this image. And another one sticks out the bottom. That's our other terminal. And so that makes up the load that we're going to discharge the Thyratron with through this through the output of this capacitor, and just cram as much current in here as we possibly can at superconducting temperatures. Now we have to have the magnet on for the time that it's going in transition, our superconductor, through its phase of not superconducting to fully superconducting, so that it locks in the field created by this electromagnet. And that's what those batteries are for. They're going to supply somewhere around 30 amps or so into this coil for about 1 minute during that transition phase to lock the field in.
Sweet. These batteries, by the way, are straight out of our scrap pile.
And what are we using to take measurements? Are we just going to look for observable effects, any kind of observable effect at this point, and then before we set up anything to take data?
Right, because this is it's such a fringe type of experiment, and there's so little known about exactly what makes it work and what doesn't. Now multiple laboratories have attempted to replicate this work and have failed for one reason or another. And so seemingly the only people that can get this to work are the inventors themselves, that be Pohr and Podkanoff. So this is more of like an unruly combination between Pohr and Podkanoff, because we're not using Pohr's proprietary mixture of superconductors and Josephson junctions. We're using more of a Podkanoff style mixture where we have 2 different superconductors where Josephson junctions are formed between each plate and the connection between the 2 superconductors. And also, like Podkanoff, we're using a slightly higher voltage, 35,000 volts in this case, instead of Pohr's much lower, 9,000 or so. So we're going more on the high voltage side because we have a Thyratron, which has given us that voltage rating, and because we're going to get a little more current through this thing at a higher voltage.
No, we're trying to put together the Podkanoff demonstration, and we're literally minutes away from doing this.
Yeah, Podkanoff Pohr. It's hard to call it either one.
I'm not really sure what we're going to call this, but it is what it is. You'll see all the components, and you call it, what's today's date? January 6th. It's a January 6th, 2021 experiment. Jeremiah, ready?
We're going to get some high voltage armed up here in just a moment.
How about I test the electromagnet first?
I would highly recommend testing your circuit first.
Okay. I'm pretty sure it's going to work. But,
I'm pretty sure it is too. Here we go. Try again. So you can see the field that's going through there. We're pulling about 35, 36 amps right now, which is not bad. That should create a sufficient field to polarize.
How many turns is it?
I have literally no idea. As many as I could put on there by hand until I ran out of space. Pretty much. Okay.
So it is what it is. Now all we got to do is put in the liquid nitrogen and get the high voltage going. So we need to move this to the center of the room. So
all right,
just give me a little space.
We just want to confirm that we measured and actually, definitively measured. And so they probably weren't actually, were actually made several times before, but we actually never detected that we're actually very with the measurement.
I like a thermos full of liquid nitrogen in the morning.
Because now we're able to
liquid nitrogen. It's almost full.
A lot of these condensed matter states.
That's gonna be enough for the entire night. For now. Okay.
Yeah, that's better.
I'm not sure if that's coming out the bottom.
Yeah, it might be. I don't know where it is going, but I can
Well,
see.
it is. It is. I feel it. A little bit is coming out the bottom.
Okay.
It is.
Okay, let's just do it.
No, we still have to cool it down. It's still not superconducting. We're losing it.
Okay, so just get on the high voltage. The high voltage ready. And we'll do it.
Man, just fill it up all the way. Yeah, look at we're seeing it in the tray. We're losing it now. Now it's actually opened itself up. I hope this is enough.
Okay, we're generating heat here from the coil, so we got to really do this fast.
Well, as soon as that, it's got to stop bubbling. Otherwise, we know we haven't hit superconductivity.
We're getting there. Definitely getting there, but I don't think it'll stop bubbling because we're generating heat.
It should be not bubbling from the inside.
Okay.
I don't know how we're gonna tell if
It looks like it's bubbling from the outside. I think it's ready. Just go. Just go. Just power it up.
Okay.
It's fine.
Stand by.
Wait.
Fill it up and then all clear.
All right, we gotta wait for that. That liquid's all moving on the bottom now.
Yeah, we gotta stop that. We gotta turn off the light over here.
Put something under it to catch that.
That's okay. It's still got enough in it to actually go through the process. That's fine. The smoke might be blowing away too. That could be kind of cool, Kevin.
You have to get the.
Don't worry about that. Don't worry about the catching that. Just the smoke on the tray there may actually be useful to analyze whether it's working or not.
Okay.
So let's just zoom back so we can see both. You can't be anywhere near that.
Back.
You have
I
to
want
weigh
to see
that.
both.
This is a high power pulse system.
Oh, there you
Don't want that camera anywhere.
No.
Okay, we're way buried. We're still good.
Okay. All right, we're watching.
Just a little more.
Just a little more, and then we're gonna fire it. We're gonna see if we get any effect on down there
Okay, it's
underneath.
filled up. Okay. Whenever you're ready.
Stand by. We're gonna start out at a little bit lower voltage. We're gonna go to about 5-6 kV.
1 second. Let me get a close up on this.
Stand by. Give it a charging current. Oh wow. That's a lot of
Wow, I can see that. That's cold.
That's 10 kV. And stand by. We're going to try to trigger it. This is at only 10 kV.
All right, safety glasses on.
Ready?
Ooh. Whoa.
That's why I said safety glasses on.
Powering down. We may have just blown our top plate off. We're going to find out in just a second.
Oh my God. Okay. Was there any shake though on the water before the shake of the
I didn't even
explosion
see, man.
Oh, we shattered our whole container.
I jumped a mile. We
happened?
shattered
Oh my God,
that
look
whole.
at that. The container just fell apart.
Yeah,
At
it
least
did.
telling you we're seeing the water on the camera feed though, because I wasn't able to look at that. So we don't
We
know.
could. We got it on the camera.
Wait,
feed.
is this- Everyone likes a good explosion. We're going to go by the frame by frame on that. Oh, here's that picture again. Okay, that's going the wrong direction again. Okay, so here's the frame by frame. That's that's when the Thyrotron fired. Here's when everything blew up. We didn't see any movement on the water, but we're not so sure if we got the Josephson junction right. And Jeremiah, if you can chime in, you could talk about that a little more. Here's the next picture. So these are literally frame by frame of this experiment going down.
So what we discovered is that making a Josephson junction is not an easy task at all. We thought it was just simply a very thin layer of material between the two superconducting faces, but what we discovered is that superconductors have a really interesting physical property around them. They have a field which appears to be capable of interacting with, oh shoot, give me just a second, guys.
Okay, we lost Jeremiah there for a second. So basically, Josephson junctions are sort of like semiconductors that would allow you to get all of the energy or all of the potential from one superconductor to the next almost instantaneously. And that is not what we got here with this experiment. There was burn through points, and I think the pictures for that were shown a little earlier. They were out of order, but there was burn through points on this experiment, and it didn't work properly. So I can go back to find the burn through pictures. They were, oh, here they are, yeah. So this is the burn through picture. That is one of the plates, and I think that's the same plate. You can see where it's burnt through. Those three, or yeah, I think there's about 3 points where it just burnt through the connection. The same thing happened in between the two superconductors. Here is the piece of PVC. It exploded outward. Another interesting thing is that I don't think there was enough thermal expansion of the liquid nitrogen to create such an explosion that would have broken the PVC. But on the other hand,
guys, I'm gonna run. I gotta run just for like 8 minutes. I will be back in 8 minutes. If you can just hang on and continue on, Mark. I'll see you guys shortly. Sorry for delaying my segment of this.
yeah, I'm just about done, but we'll just start a Q&A, I guess.
I'll be right back. So I want to show you guys just to kind of go over what I'm going to go over, so people don't leave quite yet. I'm going to show what I have done on Richard Van Durick's static displacement field drive, where I've gotten with that, and some of the test measurements that I've taken. I don't have the system fully assembled. I wanted to also go over to Boyd Bushman's magnetic beamer system, what I did with Electrats here, Frolov's hat, and then I wanted to talk a little about the 3M invisible wall. And you guys should definitely stick around for the 3M invisible wall. So if you're thinking about leaving, but you can stick around, please do, because I have a live demonstration if we can squeeze that in. Sparking, arcing is always fun. I agree with Mark. And we also can show you some test measurements on the oscilloscope at the same time. So yeah, do stick around for that. I'll be back shortly. Thanks, folks. Sorry to delay my segment here.
Okay, so Mark, let me jump in really quick. Why don't we do this then? Why don't, after you do your presentation, we will go to Q&A, and then after we're done with the Q&A, we can do Jeremiah's stuff. And then I think that after that, we just go to maybe open discussion.
That's a great idea. I'm pretty much done my presentation right now, right when he said that, so that works out perfectly. Another consideration about the breaking of the of this plastic PVC pipe is that it probably gets very fragile at liquid nitrogen temperatures. So it's kind of hard to say what caused it to explode. Was it thermal expansion of the nitrogen? Was there a force there? It's kind of hard to say what exactly we saw, because it could be that certain things get extremely fragile at low temperatures. And in the next iteration, we're going to use metal, which doesn't have that problem. And I'm going to stop the share right now because this is complete.
Okay, and I just removed the spotlight. That way we can go into question and answer. So before anything else, let me mute you back out. Let me mute everybody back out. I'm going to put on gallery view. Let's do a big round of applause for Mark. Thank you, sir.